So I'm Jack Wells, Director of Science from the Oak Ridge Leadership Computing Facility. In brief, these are the topics I want to touch on today. I want to give you an introduction to our leadership computing program, because I think it's important that you understand the voice with which I bring, the perspective that become my colleagues and I in the so-called US DOE Leadership Computing Program. And then I'll spend the first part of my talk trying to summarize for you the Titan project as it relates to the topic of our day, right? And so the role of OpenACC in application readiness and early science activities. And then I'll pivot and try to look more to the future and the way we see compiler directives, OpenACC, and others contributing to our future and how we hope to engage in the community. And I hope this is an adequate framing for our day's discussion. So what is the Leadership Computing Facility? Leadership Computing Facility is a Department of Energy Office of Science program at Oak Ridge National Laboratory and Argonne National Laboratory. Its mission is to provide the compute and data resources required to solve the most challenging problems. So in brief, we build the biggest computers we can that are production supercomputers, and we give the time away to those who deserve it based on merit review, right? So that's basically the model. It was established by the DOE High-End Computing Revitalization Act of 2004, which was a rather direct response in this country to the Earth Simulator's announcement in 2002, right? So this is the Leadership Computing Program. This two-center, two-architecture strategy that DOE has initiated and is executing is needed to address the diverse and growing computational needs of the scientific community, and also the architectural diversity that we have in the sense that different kinds of algorithms and applications may more readily go on different computers, right? So this is a very aggressive, very forward-looking strategy that DOE is executing. The time is allocated through highly competitive user allocation programs. The most visible are by the acronym INSIDE, and ALCC. INSIDE is managed at the labs, one call per year. ALCC is managed by our sponsor, DOE Office of Science. Again, one call per year. These are oversubscribed, highly competitive resources. There are typically 10% of the resource held in reserve for discretionary use, and that's where most people get their first taste of running on these big machines. Projects typically receive 10x or 100x more resource than they would receive at other centers. Say, for example, on your campus center or at a regional center. The idea is that we give the time away in big chunks. So we don't build a big machine and allocate it to many small projects. The lion's share of the time goes to very large projects. These are millions of dollars, $2 and $3 million worth of computing time per year if we were to put a price tag on it that is allocated, right? So there's a motivation to use it urgently and effectively. And an important part of our program is that we partner in a very intentional way with our users through scientific computing experts who are resident in our centers, both at Argonne and Oak Ridge. At Oak Ridge, we call them the scientific computing liaisons, and my colleague, Cray XK7, is the leader of that group, and he's in attendance here today. So if you're interested in talking about our advanced support method, Cray is here. At Argonne, they call this function a CACDS, organized slightly differently, but the idea is that when you win one of these large allocations, you get a liaison as your advocate for the center, and hopefully for the success of both sides as a scientific collaborator, right? So this is our program. Today at Argonne, there's the mirror machine, which is a large Lugin cube, and at Oak Ridge, it's our opportunity to operate for our users the Titan Supercomputer, which is a large Cray XK7. So any questions about that? This is what we mean by the phrase leadership computing. So well known to this community is the recent hardware trends where Moore's law scaling has been still active, providing us greater density of transistors. But the end of Dennard scaling, that the ways we use those transistors has definitely changed. Right? Because of thermodynamics, the single-thread performance is now flat, the frequency is flat, the power is up, each socket is emitting 100 watts or 200 watts or maybe 250 watts, and it's unlikely to go higher, and we have a number of cores. So we have the situation where some in the community have said computers are not getting any faster. You may even say they're getting slower, but they're getting wider. And it's this parallelism that we have to deal with, and it's the backdrop for much of the discussion we have today. Nevertheless, in 2009, when we were planning the upgrade of the Jaguar supercomputer, and we polled our users and say what their requirements are across broad areas of science important to our center, more peak node flops was the #1 requirement. Right? Other requirements are, you see red in a lot of other categories. Certainly memory is important, bandwidth is important, but in 2009, peak node flops was the requirement, #1. So how do we as a center meet our mission need for 10x more computing capability than we had at the time, when the #1 criteria is more flops per node, but single thread performance isn't going up. Likewise, so if I frame it at the systems level, the power is the problem. So this is a picture of Jaguar. It was the #1 machine on the planet in 2009. The peak power was the peak performance is 2.3 petaflops. The impact number was something like 1.7 petaflops. And it basically consumed around 7 megawatts when it was fully loaded. This is the amount of power similar to a small city. And for those who are in the supercomputing business, you know that 1 megawatt consumed over a period of 1 year is about $1 million. Right? So we're talking about a budget here for electricity just for the supercomputer of $7 million, ballpark, number you can carry around in your pocket. Right? So if it's our mission need to increase by a factor of 10, our computing capability, say by the 2012-2013 timeframe, when we needed to upgrade our system and do that, this computer has a black face because it's one we did not buy. Right? This computer is not present in Oak Ridge. Right? But it would have been, in order to achieve something like 20 petaflops plus, it would require something like 30 megawatts and required a footprint 4 times the size of Jaguar. Jaguar was already almost the size of a basketball court, right? And we didn't have room or power to do this or budget, right? So this was hardly an option, right? This was, if you will, the evolution of the architecture that we had at the time. So what we chose to do with our partners, our vendor partners and software partners, is to adopt a hybrid architecture for the nodes, to add more compute power on the node. So in this case, our vendor partners and we selected GPUs as the way to get more focus on operations per node. And so in addition to Cray and AMD and the rest of our partners, now we add NVIDIA, right, at the end of the life of Jaguar. The architecture changed significantly so that we changed the name of the machine to Titan, but it was an upgrade in place. That is, we used the same cabinets, the same backplane, the same wires, and we gave it a brain transplant, if you will. We took the boards out and put new boards in, right, effectively. And now the task becomes expose more parallelism through your application in order to take advantage of these flops. You want to use the right type of processor for each task. We still have in mind that we're building general purpose supercomputers, right? But we have now latency optimized cores and throughput optimized cores, and we have this extra complexity. Data locality has always been important, but it's now even more important, right? So the GPU has high bandwidth to local memory, and it has a large internal cache, but today, on today's architecture, as I'll say, the connection between the two is not high bandwidth. So explicit data management, explicitly manage the data between the GPU and CPU, at least in the early the architecture, this is how one achieves high performance. So this is a diagram from the Cray company showing the Cray router chip and 2 nodes. If you focus on the right-hand side, you see that each node has the AMD processor Opteron connected to the hypertransport, and then the NVIDIA GPU connected to a PCIe Gen 2 bus, right? So most of the floating point operations are on the GPU, most of the memory is on the CPU, and the connection between the two is not high bandwidth, right? So this is the programming challenge, right? How to manage this. If you roll it all up, you end up with a system that fits essentially on a basketball court that has 18,688 compute nodes in the whole system. So 200 racks, each rack has 24 boards, each board has 4 nodes, add it all up together, 18,000 nodes. So it's a very large system. If you will, the achievement, the systems engineering achievement is that in this same footprint, we've achieved 10x or up to 10x increase in capability for essentially no increase in the power budget, right? So our power budget in practical terms has not increased. It's within the fluctuations. For an individual run, if you're fully using the GPUs, you'll see a modest, say 20% increase in the power trace. But as a program operating this as a resource, our electricity bill has been flat, right? So this is significant. When we proposed this system, our sponsor originally accused us of wanting to become an experimental computing center, right? Not being a production supercomputing center. And if you think about it for a moment, there's about a factor of 10 difference in the budget one might expect for these activities. So we assured them that we intended to be a production supercomputing center. But as a result of that conversation, we created in our center, in our program, something called the Center for Accelerated Application Readiness, CAR. And this activity, if you will, is really the heart of the center. Or if you will, it's the heart of the way we learn how to operate a new center, because we have to recreate ourselves about every 4 years. So in CAR, we created the application partnerships as part of the Titan project to help prepare applications for accelerated architectures. Said another way, we had to prove to our sponsor that our applications were going to run on this new architecture, right? And we had to go through formal reviews of our plans for this, just the way you would do a project in urban value management. And several of the people who are part of that are still in the room today. So we created application teams to develop and implement strategies for exposing hierarchical parallelism for our applications. We had the goal of trying to maintain code portability across modern architecture. This is a goal. And ideally, we would learn from and share our results. For example, the activity in CAR then becomes the basis for our training activities that we would offer to our users. So we selected 6 applications from across different science domains and algorithmic motifs, trying to get a distribution in algorithms, in difficulties, in risk, approved by our sponsor, and then we move forward. Right, here are 5 of these applications I highlight today. And they come in material science, the community atmospheric model for climate science, material science, the LAMPS code from Sandia National Laboratory, skipping for a moment down to de novo, the radiation transport code from Oak Ridge National Laboratory to help design nuclear reactors. And last but certainly not least, the S3D code, the Sandia combustion code, to understand the basic science of turbulent combustion using the direct numerical simulation of the Navier-Stokes equations coupled to reactor chemistry. And it was this code that, if you will, that was the most important in the project for the development of the S3D, for the OpenACC compiler directives. And John Levesque, present here, was very much on the cutting edge of working with us on this program. So there are 3 ways to program these hybrid architectures, and we're basically here to talk about the directives-based approach. Libraries are, if we have libraries, that's a reliable programming model that we can advance portability. That's a different topic for how do we get the libraries we need, right? And of course, we have the programming languages that are an important part of the ecosystem as well, mentioning CUDA and OpenCL. But we're here to talk about compiler directives. So why choose high-level directives? Oops. So this is, if you will, a top 10 motivation for why we're doing what we're doing. Well, one, preserve the serial code. Application scientists want to be able to read their code. They want to be able to train their students based on a readable code. So that's important. Incremental programming reduces risk and cost. As I'll mention in a moment, for several of our projects that are using OpenACC on Titan, this was critical for them to be able to overcome the initial barrier to get started, to get off, to stop sitting on their hands, if you will. Portability. Do not commit to a hardware platform specific to dialect. This is increasingly important for our sponsor, so it's increasingly important for us, right? But all of our users will run wherever they can, right? Very few of our users will just run in one place. And I imagine anyone buying supercomputers would want to be in a monopolistic purchasing environment for anything, right? So this is, portability is important. Using a standardized approach is very important. Focusing on specifying parallelism, modest implementation. This is the key task for the future, is understanding our parallelism and understanding how we express it. This approach does not require changing the code base, language. It avoids mixing languages and can use libraries. It allows maintenance of a unique source code. I talked to a lot of users when I interview them about their situation and their view of the future. About half of them tell me, I'm developing 2 code bases right now and I don't want to do it. If you can do anything to help me avoid developing 2 code bases, I'll be very, very grateful, right? So this is a very important thing. Does not create dependencies on a runtime library. Certainly there's a lot of research going on in runtime libraries today, but when I talk to the users who are involved in this research, this is not their production code, and they can't always read the code either, right? So they have to sacrifice a lot. So often these are pilot studies. In essence, we need the runtime environment to fit in underneath the source code and the compiler environment. So, and ideally this would ease the interaction between application, compilers, and tools. So there's a lot of reason for going in this endeavor that you all are pioneering, and that is very important to our future. So when we formed our application readiness teams, we did it with what we call a 3-legged stool. We would always have a lead scientist or researcher or lead developer that we think is our application partner, our user or our proto-user for the future. We would have a member of our scientific computing group, and then we have a member of the Cray Center of Excellence at Oak Ridge. So the Vendor Center of Excellence, John Levesque is the director of this for over 10 years. And this included our members of our partner, NVIDIA. So Jeff Larkin, also present today, was very active in this. So each of these teams that we talked about had these contributions from this 3-legged stool development teams. And each of the application teams chose their own approach to managing the offload. And we've already mentioned it, if you will. S3D was all in on OpenACC. So here's my 1-slide summary of OpenACC, of S3D. It's the direct numerical simulation of turbulent combustion. It's a code associated with the research program of Jackie Chen at the Sandia National Lab. Solves a compressible Navier-Stokes equation on a finite difference grid using the Runge-Kutta explicit integration and 3D domain decomposition with non-blocking MPI. They do not run this code to, for example, simulate engines. These are more like jets, more fundamental, simpler geometries. These codes do not include the complexity of an engineering system. The idea is to understand the science of combustion, for example, that can be used to validate the subgrid models for approximate solutions to Navier-Stokes like large eddy simulations. Right, so this is the way, this is the position this code has in our ecosystem within the DOE high-performance computing strategy. So the science target is increased chemical complexity and increased resolution, increased Reynolds number. So on Jaguar, the chemical complexity was interesting from the science perspective in the sense that they would use these so-called foundational fuels of hydrogen, syngas, ethylene, but the complexities engaged by moving to more realistic transportation fuels are significant, right? And it involves more floating point operations in the chemical reactions network, and it's a very good target for acceleration. So the team identified this along with increased spatial resolution as the science driver, right? Again, the porting strategy involves taking a flat MPI code, first creating an MPI plus OpenMP code to refactor, expose more parallelism, and then use OpenACC for the offload. So all intensive calculations that are possible are moved on to the accelerator. So most of the work is happening on the accelerator, with some redesign and message passing to overlap communication and computation. So, the performance on Titan. It should be emphasized that this was the first large-scale production code written in OpenACC and implemented on Titan. From beginning to end, it realized a 7x increase in total capability for the car effort. So in moving the code from Jaguar to Titan, a good summary of increased capability is 7x increase in time to solution. Okay? And notably, a theme that returns is that the refactored code early in the project was already 2x faster on the Cray XK7, that is on the old machine. So this is a theme that returns. You work on your code to expose more parallelism. The result is it runs faster on the hardware you already have in the room. Okay? So in addition, since the end of the car project, Jackie Chin continues to base her development on this code in the context of her Exascale co-design project called Exact, and by adopting the Legion runtime environment with collaborators from Stanford, they've achieved an additional 2x increase running at scale on Titan. So the work continues, right? And it's a lot of work. So that the word easy doesn't appear on this slide. Okay? The word easy doesn't appear. Right? And we do ourselves a disservice often when we say something of this magnitude is easy. If it was easy, I guarantee you the national labs wouldn't be doing it, right? Somebody else would be doing it. Right? It doesn't mean everything about this activity is hard, right? But it's unapproachably hard, right? But we shouldn't kid ourselves. Okay. So some comments on the broader utility of porting to accelerators. By doing so, you better understand your code's challenges in general for the mini-core architectures. This is a rephrasing of the statement. Understand the parallelism in your application. You often want to end up refactoring your algorithms unless you're very fortunate in the way the code was structured. And refactor the algorithms in a way that you realize more floating point operations with less data movement and fewer data dependencies. Right? You may even change the way you thread, which would, again, help on any architecture for the future. Higher level hoisting of the OpenMP allows more parallelism, more data-independent work, more flops. Right? And again, just make the point very clearly, changes incorporated into the CPU code will result in faster CPU code performance. This is something that we've observed across the spectrum of application teams of which we've been a part. So, and this may affect one's perspective on code refactoring as a cost-benefit analysis. Okay? So this is from our experience. So, John and I were in the airport yesterday, waiting on our plane. It was delayed a little bit, so we had a few more minutes. So I made a mental list of applications using OpenACC on Titan today. I expect that my colleagues have already thought, if they looked at the slide, they've already thought of code that I've forgotten. So this is not intended to be an exhaustive list, but it's intended to be somehow representative of industry-relevant codes. Many of these codes are coming in combustion or in turbodynamics. So there's a lot of interest emerging from manufacturing sector, turbo machinery sector, and to taking advantage of modern HPC. Much of this has been driven by the opportunity they perceive for gas generators. They see a huge market opportunity in the future to improve their competitive position, their efficiency in terms of the gas generator market, and they're putting resources and software engineering in that direction. So again, CAMSC, this is the community atmospheric model. This work is, the work I'm familiar with is going on in our center. The point of contact is Matt Norman. Tacoma is the design code for turbo machinery at GE Global Research. The point of contact is Brian Mitchell. TipStar is a research code from the University of Southampton in the UK. And it happens that this is a DNS code, and GE is investing in this research group. United Technologies is investing in the Leslie code, which has its origins at Georgia Tech. Fine Turbo is the design code by NUMECA, and it's being used by a small company called Ramgen that just was recently purchased by Dresser Rand, again for turbo machinery work. And there's a very exciting chemistry code in our Insight program at Oak Ridge that's using the Cray compiler to do quantum chemistry calculations led by the distinguished chemist Paul Jorgensen from Argus. So I just want to highlight a couple of these projects. So this is the project led by Dresser Rand and NUMECA, their independent software vendor. Again, the code is called Fine Turbo, and it's a design code for designing a turbo machinery. It's a CFD solver toolkit, big complicated code that had its origins in the early 1990s. No clear separation of logic, program flow, algorithms, data structures. Data was organized in a monolithic integer and real vectors with complicated interrelationships. They have a single code base. They don't want to fork the code for maintenance and other reasons. And they need a single solution for GPUs and many integrated core architectures. And the GPU development must play nice with the solver development. That is, their solver is under continual development, and they can't fork the code because of that either, right? So 2 years ago, these people looked at the landscape of accelerated computing and decided that there was nothing there for them. No, they didn't do anything, right? But they had one customer, this Ramgen company, small engineering company from Seattle, who kept pushing and funding some work there and got them to help them with a project on Titan. And they did what many people would do, is that they decided, well, we can't rewrite the whole code, especially not for what you're going to pay us. So they adapt a model of focusing on one expensive component in the code. Of course, OpenACC or other directive-based approaches will allow that, right? So they targeted a component called the CPU booster module, and the refactoring of that module resulted in an overall increase in performance for the whole code of up to 20 to 40%. They were very happy with this. They did not expect this from the beginning of their approach, and so they were optimistic and were encouraged to continue looking at other modules in their code. So the development here is ongoing, right? John Levesque and Jeff Larkin have been consulting with these good people, and if you want to read more, there is one talk online at the GTC 2004 meeting by David Gutzweiler, and actually Ravi Srinivasan from Dresser Rand is giving a talk on the floor of the SC course on this topic. So this is an example of where a company has had a recent changed attitude about their code development plans because of OpenACC in the context of our user program. Right? I thought it was relevant. Another example from turbo machinery, this one from GE Global Research. The point of contact is Dr. Brian Mitchell. This is their design code. Tacoma is their design code for turbo machinery at the GE. And so they want to understand how can Tacoma be prepared for these modern architectures and utilize hybrid accelerated architecture. The strategy is to work on loop level optimizations and improve data motion optimizations. The code, they've worked with us for a few years to scale the code up to more than 100,000 cores, either in strong or 200,000 cores in weak scaling. Their current efforts with GPU acceleration, they've achieved a 40% increase in time to solution, and they tell me they can see a path to a 70% increase, right? So they consider this good results for the level of effort they put in it, and they are encouraged about the path forward. They were sitting on their hands with this code, complaining about hybrid accelerated architectures until recent years, right? And I think it was the directives-based approach that gave them a path to get off the dime and start doing something with their application, to explore these directions. So we view these as successes. We're happy to be a part of such successes. And of course, the Vendor Center of Excellence has been a big part of this story. So shifting towards the future, when we field one machine, we immediately start planning our next machine. And so for 2 years, we've been working on what will replace Titan, right? And this is just saying we have Titan. It was put together in 2012. It was accepted in 2013. In 2017, we expect to be building another machine that will ultimately replace Titan, right? And in order to meet our mission need, we need to be somewhere in this range of total performance, 100 maybe to 200 petaflops total performance. And I don't have too much in the way of details to talk about this machine today because we still haven't signed all the contracts and all these kinds of things. But this is where we're going, right? In order to meet our mission need, we have to push forward to the future. So, accelerating the path to exascale. Accelerators are of interest because they offer high ratios of performance to power, as we've already talked about. And at the exascale, regardless of the vendor or the architecture, we expect extreme levels of parallelism. Heterogeneity is a concept that we'll likely be dealing with. Maybe lower memory per footprint per core, certainly deeper memory hierarchies, high cost of data movement, and extreme power constraints, right? Our sponsor has given us guidance over the next 10 years. We're to plan to have a power budget of less than 30 megawatts for our program. That is, she's not going to pay for more than 30 megawatts of electricity, right? And so that's significant. And today, if you look at the landscape of top systems, several of them are based on the accelerator concept in terms of the way they manage, the way they architect solutions to the challenges I've tried to outline. When we repeated our requirements gathering process in 2013, many of our users told us that there is still a moderate to large amount of parallelism in their applications that could be extracted. Right? They're the best ones to know. But they also told us, maybe even more strongly, that they rated the difficulty in expressing this parallelism as moderate to difficult. So this, for us, this underlines the need for more support, more training, more assistance, more community activity in this topic of expressing this parallelism. So it came out rather clearly even in our formal application requirements process. And I don't know how significant you might make it, but for the first time, floating point operations was not the #1 ranked requirement, in the sense that a memory bandwidth nudged ahead in the overall quantitative ranking that we executed when we did application requirements. So flops per node is still a very high requirement, but it's being surrounded by memory bandwidth, which is the way the architecture will work anyway, right? So many of you all know a tremendous amount more about OpenACC than I do, but I'll try to frame this at least from my perspective. So OpenACC, of course, is a directives-based API that programs accelerators in C, C++, or Fortran. You all define the standard in some sense. The goal is to express the data and computations to be executed on the accelerator incrementally is a possibility. So you can do this with incrementalism. The main OpenACC constructs are parallel and kernel regions, parallel loops, data regions, and a runtime API. And here's a more, if you will, expanded view of a CPU or latency optimized core or a throughput optimized core. Right? So the challenge for accelerators is moving data across the CPU to accelerator with the different memories. How to specify the complex data structures to the accelerator, how to achieve a consistent view of data between the accelerators and the host. This is a high-level statement of the fundamental challenge. So, more specifically, how do we specify the in-node parallelism in the application? A loop-based parallelism is often not enough for all the parallelism that's available on the node. So we have to go deeper into find more parallelism. How do we efficiently map the parallelism of the application onto the hardware? How do we schedule work to multiple accelerators within the node? How to schedule work within the accelerators while being portable? Often these things are constrained by the specific architectures. How do we transfer data across the different types of memory? This problem may go away or be somewhat ameliorated by architecture, but it's still important for data locality. And how do we specify the different memory hierarchies in the programming model? This is a challenge for the standards community. So to make the point more explicitly, we have two versions of memory. We have the accelerator region on the CPU and then the GPU more on the when we say accelerator. We now have two copies of this data, and we have to keep up with it. That is, we have to do some bookkeeping. This is another one of the challenges. So we have a computer science group at our laboratory that's part of our center that's very much engaged in these questions and in requirements, requirement gatherings. And they're engaged with a large number of applications that are running on our machine or may be running on the machine in the future to try to understand their requirements, their data structures, and to look for interesting cases that can inform the standard. So this is the co-design process between the applications and the compilers. And it's our intent to be very much engaged in that conversation. So at our center, OLCF, the Oak Ridge Leadership Computing Facility, our plans for OpenACC as a programming model, it's been a key part of our strategy for portable programming of the heterogeneous systems since early on in the Titan project. There were several implementations of OpenACC, the PGI, Cray, and these are our partners. We'd rather have more than just one for risk mitigation, for sure, right? Multiple outside options to increase OpenACC support. GCC is a new option. Petascale is an option. And then several research compilers like the one at the University of Houston. These are all part of the ecosystem that we view as very important. Our vision is for more simplicity, if you will, that eventually there would be a merging of OpenACC capabilities into OpenEP, but we certainly can't make this happen on our own self, right? So this is a broader community issue. But there is some reason to think that this is a reasonable idea. If you look at OpenMP and OpenACC as they develop, OpenACC innovation continues, and many of the good ideas that have emerged through OpenACC have been adopted into OpenMP. So this is just to indicate a timeline for OpenMP and a timeline for OpenACC, and how the interesting ideas pioneered in OpenACC have been adopted by OpenMP. Now, so obviously the programming models need to continue to evolve before they can stabilize. And at this point, it's good to remember that neither of these compiler standards is a panacea, is a magic wand, right? And the code refactoring that we talked about earlier on in the talk is really going to set the upper limit on what can be achieved. That is, the degree to which the application can expose that parallelism, right, will determine how much benefit the application achieves once that offload is managed through either one of these standards, right? So this work on code refactoring is important. Of course, that's the expensive part of it. In the Titan project, we estimated that 70 or 80% of the effort, and therefore the cost, was actually applied to code refactoring. And it was only the minority part that was actually involved in programming the offload function. And one more thing. I'm almost finished. as we go forward in the future, we're not in a position where we can talk openly, but this Center for Accelerated Application Readiness is central to our center. And so as we execute our new project, we will have a new version of the Center for Accelerated Application Readiness, and Cherk is leading this activity. As a significant difference, after the announcement of the OLCF 4 project to replace Titan in 2017, we will issue a call for proposals for application partnerships to work with us, if you will, in recreating our center in and around this new computer, right? And so, and again, we will use the same approach of this three-legged stool that will use a component from our center, from our application partners, and the vendor center of excellence, with the goal of performance analysis of the applications, creating a technical plan for the code restructuring and optimization, and the deployment of the applications on OLCF 4 early on in the life of that new machine, right? And it will be this experience that will inform our training, our documentation, if you will, the full scope of our center. So here I will conclude. So I think that these are the points I want you to take away from my talk. So leadership computing is for the critically important problems that need the most powerful compute and data infrastructure. Accelerated hybrid multi-core computing solutions are performing well today on Titan on real complex scientific applications. I've only highlighted a few, but there are many more, right? You must work to expose the parallelism in your codes, right? And this refactoring of codes is largely common to all massively parallel architectures. So, as another anecdote on this point, there are important applications that were written for our sister facility's early science program. That is the Argonne Leadership Computing Center's early science program. They worked hard to get a certain number of applications running there. Many of those moved over to Titan. There are examples of one graduate student working for 4 weeks to get their first full-scale run on Titan. Right? And the reason is because the parallelism had been well exposed on the other resource. That one smart person who understands something about the accelerators, learning the programming models, was able to get full machine runs on Titan that actually contributed to a Gordon Bell paper in 2013. Right? Of course, they improved things over the summer, tweaking things and getting another factor too, but it wasn't a large barrier moving that code from Mira to Titan. Now, in order to use Mira, you have to expose the parallelism, right? So if you haven't exposed your parallelism, that's where the work comes in, right? So OpenACC compiler directives are enabling complex applications relevant to industry to take advantage of this hybrid architecture. And we need to advance the compiler co-design to satisfy both the application requirements coming from our users and the requirements that are intrinsic in these modern computer architectures. And I think that's the topic of our meeting very much. So with that, I want to thank our users, in particular in this talk, Jackie Chen, Brian Mitchell, and Ravi Srinivasan, the Titan CAR team listed here, our vendor partners, Cray, AMD, NVIDIA, CAPS, Linea, PGI, and this work was funded by the Department of Energy. So with that, I'll stop and take your questions.
Thank you very much. So we have time for a few questions.
Simple one. The total runtime for S3D.
Excuse me?
The total runtime for S3D.
This the runtime environment on S3D.
Yeah, the S3D run like one process. Like take weeks or months.
Oh, the time to run.
Yeah.
Oh, one production run for science would be of a scale of something like 100 hours on big chunks of the machine. You know, a third, a half, or 2/3 of the machine, depending on the problem size. But yeah, these are explicit time stepping simulations, so it requires some length of run.
That's a question. So the codes that you actually worked on with Clara, I would characterize as people who are coding in Petascale, they're not the same. I was wondering, how do you choose the applications that you work with in this manner?
So, for the Titan project, indeed we did choose them. And we chose them with an eye to spanning our workload, different applications with a strong emphasis on the Office of Science workload applications. Getting a span of different algorithms. If you can think about it, we wanted to have check marks on at least all 7 of the Berkeley dwarfs, right? This approach. And then we wanted to have a spectrum of risks, degrees of difficulty, because the performance on these codes were hardwired into the acceptance document of the computer, right? Going forward, we have all those things in mind, but we're going to do something significantly different in that we're doing a call for proposals that we didn't do last time. And the goal here is to make sure that we're getting the right projects, the ones that have the best opportunity for impact, and to make sure to emphasize the fact that these are really partnerships between the application scientists, the application development team, and our center and the vendor partnership. So people are not going to be drafted to do this, they're going to apply.
One quick one, I guess. In the oil and gas industry, if you look at algorithmic development for different kinds of, let's say, reverse time migration algorithms, as we move forward more complex algorithms, say least squares and so forth, you see a lot of the ISVs within the industry developing their own particular flavors of those codes. I'm just curious how we would be able to use partnership like what you were talking about in order to be able to look at general purpose versions of some of these kinds of codes in order to be able to then percolate them back into the ISV community, as well as augment the efforts that are going on in a number of the oil companies themselves.
Good question. I think the way that's happening in a lot of other industries is through the industry funding their favorite university-based or laboratory-based scientists for some open component, some forward-looking component of the work, right? And then partnering with that in the context of that open research with us, it can be the best way. And that's the way many people are choosing to do it, right? You can certainly bring your proprietary code and do proprietary work at our center. Not many people do it. One of the reasons not many people do it is that we would need to charge full cost recovery on the use of the resource, right? So about 3 cents a core hour in the current year, or $1 a node hour, right? And so, yeah, many of these other industrial concerns have existing partnerships with universities. They do that for recruiting purposes, for talent development, and also to do more forward-looking pathfinding work. It's that work that fits very well in an open environment in our center. Another way that some people are choosing to do this is by engaging with the laboratory community in cooperative research and development agreements that are focused on the R&D activities with access to the user facilities computer as one component in what is really a research project rather than a user project. Right? This will be funds in on those, some kind of cost sharing, and the IP will be negotiated in the context of the negotiation of that Cray.
Yeah, and really the reason I brought that up is that's a constant struggle within the industry, that we have needs that really would require platforms like this to be able to test whether we can scale to the heights we need to, yet the folks developing those algorithms are developing them specifically compete with each other in the same market. So you've got needs and requirements within the industry somewhat at loggerheads with each other.
Yeah, of course that's a broader conversation than just the OpenACC, but it's a really interesting one. If you compare it to, say, other aspects of manufacturing, they don't compete on the basis of the software. In fact, they all use the same software because they decided to outsource it to software vendor. That has its own problems and its own advantages, right? I think your community obviously sees more value in the computing. In some sense, you have more expertise. You've done that. I think one thing I would say is you want to be exposed to community standards. You want to be exposed to community standards. Here, let me give you an example. I had a conversation with some company in the oil and gas industry last year who wanted to consider using us as surge capacity. They'd gotten some high priority work that was going to swamp their already large resources, and they wanted to evaluate us as surge capacity. And it was all going to be proprietary. It was going to be, actually, it was a potentially disruptive event in my user program, so I was going to have to get many, many people on board. In the end, I said, well, before we go to all this trouble, let's make sure that your code will even run here, right? And we started talking about a smallest project that would just sort of try things out, kick the tires. And it became so apparent that their world was different from ours that they ended up going in a different direction in terms of their surge capacity, right? In other words, we weren't an effective solution on the time scale that they needed a solution. And my parting comment to them was, learn about what's commonly available, because we operate our center using, to the best we can, community standards, right? But their code was written in such a way that it would have required too many changes in order to work in our environment, right? So I think it's in your interest to have some exposure to national centers or university centers so that you understand what the rest of the world is doing. I think you're transitioning from a period where in the past, anything you needed, you either bought or wrote or built, right? And so very much a vertically integrated enterprise. That's my perception. And I see your industry as transitioning away from a vertically integrated enterprise to something that's more open and that has more partners, right? Which is the environment that many of us are already in, is this partner-rich environment. And so you need to think about the technical culture gap between the two. So it's a longer conversation, but that much is apparent to me. So it begins with a conversation.
One more question. In your presentation, as well as in your work at your facility, you focus heavily on legacy codes, on things that are already big and that are established customers, because I believe those are just the most demanding applications. Do you have any advice for those of us who are still writing new codes, these kinds of things that may be large in 2023, your last slide somewhere in the middle? New codes, new problems are still being generated. New equations are written. Think about compressive sensing, these kinds of things. What is your advice to a group of people, if any, that is writing a piece of code from scratch? Which rules should they abide by? Should they use OpenACC? Should they use something completely different so that in a couple of years they're not trapped by the same traps that your legacy codes are subject to?
I don't have a rule book that can answer this, but I would just say that we share the same challenge for new applications. We understand that when we collect requirements for our next supercomputing facility, if we only consider today's users as something like driving a car looking in the rearview mirror, and that there are big problems out there that are not running in our data centers today that very well should be in the future. And our sponsor values that vitality, bringing in new centers, so we get a tremendous amount of credit when we introduce new users and new communities of users to our center. Now, how does it happen? We're a use facility that allocates the resource largely on a one-year basis. So most of the effort goes to running this year's projects. But we are very interested in the development projects, and these kinds of development projects can be embraced within the Insight program in the sense that you can have a 3-year project, right? We certainly right now don't have the concept of a 10-year project, but we do have the concept of a very attractive science program that, based on the merit, deserves the resource, and we can work with them over a 3-year period. And we have those projects today, right? Again, it's an opportunity to engage and to have a conversation, and we certainly want to encourage these kinds of things. And most of that work is going on within our director's discretionary program. Within the Insight program, we would typically have about 30 projects per year. Within the ALCC program, about 20. But in our discretionary time, that 10% of the time, we would have 100 or 120 projects. And people are exploring these new ideas in there. And it's not as visible in the sense that those are not the sort of the headline topics. But we're not the I would say we can be part of the solution, but we can't be the whole solution. Fernando.
Well, and hopefully my talk will answer some of his questions.
Okay, maybe one last.
I just have one more question. Could you clarify what you meant by avoid runtime library dependencies? What were you thinking of when you said that?
I'm thinking of a situation where the runtime environment is very visible in the source code, right? When you have to introduce a lot of that explicitly in the source code, I think it would be much better if the runtime was was less visible, more invisible, and if you will, sitting somewhere underneath the compiler.